Right, welcome back everyone. Today is lecture 10, and as you can tell, we will be talking about, or like this week, we'll be discussing computer vision and including like an introduction to CNNs or convolution neural networks. And like we'll talk about the basic architecture. And on Friday, we'll cover a few case studies. And we'll see why these case studies are so important because we didn't talk about any case studies in other neural networks. And before like I keep going ahead, people who are online, can you hear me? Just type in, okay, thank you, Connor. Because usually that's the issue. Okay, so let's begin with the idea of like computer vision. In fact, I like to think about vision from the perspective of humans, right? Vision is so important. Like we infer almost everything by seeing objects, by observing them, by extracting useful information from them, be it from the object that you're seeing in front of you and making decisions based on that, or how you're interacting with other humans, all of that vision to a certain extent, right? And so the question, does that sound? I hope I didn't do anything. Okay. Okay, that's fine. So yeah, so like the idea of computer vision comes from the fact that computers need to see in order to make intelligent decisions, in order to extract useful information and make use of that, because a lot of information has a visual relevance as like compared to some data or some numbers or some text. And so the whole idea behind computer vision is that computers need to see, and then we need to understand how can we make computers see, right? And of course, like you're familiar with a lot of computer vision applications. One of them is like going into the image and tagging objects, right? Facial recognition is another. You've seen that on a lot of social media platforms and otherwise, how computers recognize faces and then tags your name with that, right? And then autonomous driving vehicles, right? They're using CNNs and they're using computer vision as an application. And like what other applications of computer vision can you think of? Like, yeah, medical imaging. That's a huge an important area of like computer vision application. So all of those are like really important aspects of computer vision and why this topic is so important. And if you look at the literature, you'll see like the last 10 or 12 years have been like phenomenal in this with the advent of neural networks, right? So earlier it was difficult, and you'll see like this image data is difficult to handle with all its intricacies, with all the amount of volume, and then the spatial structure of an image. For example, like I cannot pick up like a pixel here and then just like combine it with a pixel here because there is a spatial structure to this image and I cannot like break that somehow. So all of those things make it like extremely complex in terms of the overall model efficiency, in terms of the overall time that your model takes if you are trying to train it. And so because of that, we've come up with these special CNNs or convolution neural networks. So that's what we're going to talk about in today's lecture. And okay, so this section actually talks about this field as a whole. And then there's a paper that I've provided in the reference in the reading section that talks more about these things. But let's actually jump into the idea of convolution neural networks, what exactly these do and why do we need them. And I'd like to like think about this right from the artificial neural networks perspective. And okay, so I know that many of you are familiar with like how image data can be used and manipulated. So you have pixels, right? Every image can be divided into like something like this. Let's say I have. So let's say I have this image, and this image can be identified by the pixels that it consists of, right? And so let's say this is like an image that is like 64 by 64, right? And by the way, this is a grayscale image. So we want to continue with this convention because there are channels to every image. So there are 3 channels, and those are for the RGB, right? The red, green, blue. So if I'm just like showing you a single channel, just assume that this is grayscale. So even for a grayscale image, if we consider the number of pixels and then add to that the number of images that I need to process, and let's say I'm using a simple artificial neural network to process this. right? And like nobody's stopping you from doing that. So let me think about it. Like each of these pixels can be my input. So let's say this is going to be x1, x2, and so on, right? And then let me just flatten this out and use it as an input to my artificial neural net, like a feed-forward network. So basically, I'll have like this input layer, x1, x2, and so on up to xn, which obviously is going to be 64 times 64. And then if this was an RGB, most likely it is going to be by 3, right? And then if there were like some 1,000 certain images, and so that's going to be like times 1,000. In terms of, I'm not saying that the input is going to be 1,000, but the number of times you're going to read the input. So the point that I'm trying to make here, and then you're going to have the hidden layer, maybe multiple hidden layers, and then the output layer, and then you'll make some prediction. Right? So this is definitely doable. And in fact, in cases like the MNIST dataset, I don't know if you are familiar with the famous handwritten digit dataset. So with that, people have shown that works really well with like feed-forward networks. And reason being that as far as I remember, every image like is a grayscale and it's just 28 by 28. So that's kind of doable for an artificial neural network. Now, the issue is that as we have more image data on the web and otherwise, and we are trying to process like these huge chunks of image data, we need something more than this because of the computational complexity that arises from the fact that I have such a huge input. That's number one. The other thing, like by flattening this image, like this raw image, and I'm calling it raw because I haven't processed it or anything, I just picked up the pixels right from the raw image, right? So if I'm picking up these pixels like x1, and let's say this one was like some x100, right? And let's say this was x1, x2, and this is x3 and x4. So if you think about like their arrangement, right? If you think about their arrangement, this x1 has to be near to x4 because that is giving me some kind of information about that image. Let's say it was like a face. So then if like your eye was shown somewhere here, then this pixel and this pixel like they have some connection with one another and they should be impacting the output in a certain way. And so for those two reasons, we cannot use an artificial neural network as it is for complex image processing tasks. So that's the motivation why we need a different type of a network. So the first thing that like this spatial structure thing is the fundamental motivation behind the convolution word that comes in CNN. So this convolution is actually an operation that we perform so that we can retain some kind of like spatial structure between these pixels versus these pixels versus these pixels and so on. Right? So that's the fundamental motivation behind these. And let me just go back to the lecture notes and see if I missed anything. Okay. I hope people who are online you're able to see my screen. If not, just like let me know. Okay, so this section talks about this motivation behind convolution neural networks and why we need them. And of course, they have a lot of similarities with the ANDs that we are familiar with, in the sense that the training would happen similar to like a feed-forward network, except that the parameters would be different. And you'll have like different number of layers that will be doing some different operation. But then you'll use gradient descent and backpropagation to train these. So that's the high-level idea of a convolution neural network. Now comes the idea of like, why do we call them CNNs, or why do we call them convolution neural networks? Now, if we go back to this idea of like having an image, and as I just talked about, and like I have these pixels, right? And let me just assume that it's like a very big image, and it has like lots of these pixels. So of course, like if you take this as input, and this is my features, and based on this, I'm going to train my model or my network. This is like a huge chunk of features. And so what we try to do in like this convolution operation that I'm going to just show you is that I come up with something that's known as a filter or a kernel. So like in literature, you'll find both these words. So I come up with a filter, or sometimes it's known as a kernel, so that I can somehow extract or put together like more than one pixel together and extract all the information in that. Right? So that's the fundamental idea of a filter, that I'm putting together more than one pixel and such that their spatial structure is maintained. I'm not losing that. And then I'm coming up with like some kind of like think of this like a single neuron that has like the entire information of these pixels, right? And then maybe come up with another neuron that has like the entire information of this one, something like that. So then the first advantage of using this technique would be that my input size will go down, right? And then there is this like trick to this convolution operation that I'm somehow able to maintain that spatial structure or the spatial relationship between each of those inputs. So now let's see how this convolution works. It's a very simple thing that you come up with a filter that is like similar to your image, and it has some known dimensions. Usually the dimensions are like odd and it's a square thing. So this filter, think of this like as another image that you'll be putting on your original image, and you're going to extract some information from that. So let me like exactly show you what goes into that. Okay. Next slide. All right, so let's assume I'm working with a 6x6 image, and each like of these has like a pixel information. 1, 2, 3, 4, 5. Okay, I'm like really bad at drawing, as you can tell. Okay, right. And then what I do is I would like to do a convolution operation. And by the way, these pixels have some values, right? So let me put some random values here, like 3, 0, 5, 2. And so on. Okay. And I have to perform. So this is a 6x6 image. That's my input. And I want to like do a convolution operation on this for the very reason that I want to extract useful information or extract some useful features from this. And the other thing is that my input should go down. So like even before we look at this convolution operation, think of this as like when you're looking at the MNIST data and you have like those digits, right? So what this convolution operation, this kernel is going to do is it's going to extract the important elements of those features. For example, you can put like one convolution that is going like one layer of this convolution operation that is maybe going to pick only the vertical edges from the image. That could be one convolution. Or maybe you can put another filter or kernel. Let me write it down. This is a filter that is going to pick all the horizontal edges from your picture. So essentially, think of this filter or kernel as something that's able to extract some aspect of the image. Because now you can tell that like the way we are, think of like, let's say you have pictures of trees. Now, pictures of trees are like really easy for us to identify that this is a tree or not. But if you're thinking in terms of the pixel values, a tree has a lot of attributes. It has a lot of features. And in order to identify those features, you need to have some way of like sequentially getting its different features. For example, let's say it has like a trunk that has like these vertical edges. So let me like put a filter that extracts only the vertical edges. Okay. And then, okay, it has like some like leafy kind of a structure. And so maybe I'll put another filter that's going to extract the outlines of that and so on. So maybe have, let's say I want to have some kind of a filter that extracts the contrast in the image and so on. So there are different aspects to my image. And based on that, on those different aspects of my image, I'll have like these filters that are going to extract useful information. So just think about like this filter as just one filter. There won't be a magical filter that's going to extract all the useful information and put it together. So you will have like multiple filters. But let's see how it does that. Right? So it does that by a very simple formula that you've been using ever since we started working with like neural networks. That's going to like have a dot product of like these elements that I decided to have in my filter. Right? So let's say I have a 3x3 filter, right? And this 3x3 filter is used, let's say I'm using it to extract only the vertical features. Okay, so if I'm trying to do that, then I'll have some values in this filter that are in some ways related to the vertical lines in my image. For example, it could be that this is like 1, 1, 1, 1, 0. This is a very well-known filter. So if you think about it, right, this thing is like pointing to a very like dark part of the image, and this thing is pointing to like the lighter portions of the image. So somewhere it's going to extract the vertical lines, right? Because there's a line, and then on either side you have like some lighter areas, right? A very big, like this is not something that we use as often because there are more complex filters available. But for now, let's assume that this is going to extract all the like vertical lines, right? So let's see what it does. Now, the way I'm going to like, and then obviously we are going to get an output, right? So let's also think about the output a little bit. Now, what I'll do is, this is a 3x3 filter. Imagine that I place this 3x3 filter somewhere here. And let me change the ink color to maybe black. So I place this here, right? I overlap it with the leftmost corner. And then what I do is I do an element-wise operation. So what this is telling us is that this is an element-wise operation. For example, here, it is going to be like a column by column, meaning 3 times 1 plus 4 times 1 plus 0 times 1 plus like this 0 times 0 plus 1 times 0 plus 1 times 0, right? So each column element with each one. Similarly, like this 5 times 1, 0 times 1, and 0 times 1. So we are going to get something here, right? And I don't know what we are going to get. Let's assume that I get a 9. I'm just like assuming, right? I don't know, maybe I won't. Just like go and do the calculation. But if like whatever I get here as an output, okay, that is going to be this topmost element here. Okay, so think of this like this dot product thing or this scalar product that I just did as something that this like filter is able to extract from these pixels up here on the top. Okay, then what I do is I move a step further, and this movement is known as a stride. We are going to talk about that a lot. So I move by one step, meaning I'll put my filter like this and do the same thing, right? And then I'm going to get some value here. Let's assume that value is like 3 or something, right? And so on. So how many like steps can we move in this case? So this is going to be the third step, and then this is going to be the fourth step. So we'll have like 4 values up here, right? So maybe like 3, 8, I don't know. I just made those values up. You can go and do the calculation. Then after that, we need to fill the rest of these, right? And the way this is filled is that then I'm going to move downwards like this. And so basically I'll be putting this filter on every 3x3 matrix, moving by 1 towards the right and then moving 1 towards the bottom. And I'm going to fill this matrix 4x4. Now, how do we get the dimensions of this output? And this output, by the way, is also known as a feature map. So whenever I'm talking about a feature map, it's essentially this thing. Okay, so the dimensions of this are pretty like obvious, as you can tell from this, that I have like some input dimensions, and let me assume that I'm like denoting this by L length and width, right? And then this is like filter height, filter width, right? And so this can be calculated by doing something like this. So L minus the filter dimension, which is 3 plus 1, right? So just remember this. This is how we get the dimension of the feature map. For example, here my L is 6, right? And then the filter dimension is 3. So 6 minus 3 plus 1. And so that's 4. And usually these filters have dimensions that are odd. So for example, here it's 3x3. It can also be 5x5. Okay, but remember that the feature map, the dimensions of the feature map are given by this. And we are going to manipulate that formula a little bit because we'll also add some other techniques to how like we can capture this. But regardless, this is the fundamental idea of a convolution operation, that you have a filter or you have a kernel, and based off of whatever information you're trying to extract from your image, you are using that type of a filter. You can use multiple filters, but just remember that filters are used to capture some aspect of your picture, maybe edge detection, maybe vertical edge detection, maybe horizontal edge detection, and so on. Because if you think about it, we are actually creating these regions of activation in my final feature map that has like some relationship to the spatial structure of my input layer or my image, and like this one, like the convolution operation is adding to that as we perform it. Questions, doubts, anything? So this is pretty straightforward, right? Let me quickly go back to the lecture notes and show you a picture. I think that better explains what I'm talking about, if I remember correctly. So here, this one, it's taken from the textbook. This actually shows us what's going on. And a few more things that I'd like to add here. Okay, so if you look at the input image, it's 32 by 32. That's my image. And this 3 is actually telling me that this is an RGB, right? So that's the third dimension. And here I'm applying the filter or like the convolution operation. So now notice the filter is 5 by 5 by 3. Now always remember, so that's like a convention, that the image, if it's a grayscale, then the filter or the kernel should also be like one dimension in the sense that it should be a grayscale as well. So you won't have like this thing as 3. And this thing, by the way, is referred to as depth in many literature. And sometimes it's referred to as channels. So think about a colored image as having 3 input channels, red, green, blue. And so because if you're using like a colored image, as is the case here, right? So then you'll use a filter that has 3 channels as well, because we need like one for each. And we'll see like how that happens in another section today. But regardless, this is the output or the feature map. And in our case, the feature map was one dimensional. Remember what I did, like a 6 by 6, and then a convolution with a 3 by 3, thinking that all of this is grayscale. And then finally, I got a 4 by 4, right? So then the assumption here is that like this is exactly going to be like it's going to extract everything that's there and be like the third dimension is not going to be like more than one. But what happens is that we can have more than one filter here. I'm going to show you when we have more filters, then the third dimension comes into play here. Otherwise, it does not. So this dimension that's showing here, this 5, let's assume for now that there is like nothing here. It's just 28 by 28. I'll show you how this comes, the dimension for the feature map. So for the time being, just imagine that the output or the feature map has the dimensions like of this, like L minus filter plus 1 times L minus filter plus 1, always. Okay, so this was like an introduction to the convolution operation. Here, this is actually showing us an example where we are using a horizontal edge detection filter. So notice what this horizontal edge detection is doing. Just look at the filter itself. So you have like this region of like light or dark region in the middle, and then 2 extremes on the other side. So in some ways, it's trying to create that region of horizontal activation. So it's capturing that. And so there are different types of filters. In fact, I have like some of them here listed here, and you can, if you're interested, check. Yes. That's an excellent question. It's part of the learning process. Yeah, I was coming to that only. So yeah, of course, there are different types of filters that like, so you will initialize them with some values, and then they will be like, they should be learned from your learning process. And you will see that in CNNs, the hyperparameter thing, like setting up the hyperparameters is a huge issue because we have too many hyperparameters. So yes, and so the good news in CNNs is that enough research has been done. And that's why I have like a whole lecture dedicated to these case studies, because most likely for most, like 99% of the problems, you just use a given, like an existing network configuration. So, and like depending on the problem, of course. So yeah, that's an issue, and you'll see why that is an issue. Okay, so that was that. Let me see if I missed anything. So here I'm just talking about like the dimensions of the convolution operation. But as far as like the idea goes, the idea is that you're trying to extract information and retain the spatial structure using this convolution operation. So as long as like you remember that, think you're good, right? So as the question was asked about like, and that I like to, so these filters, usually we begin with some values and think of these as weights in my input, like when we were talking about ands, right? And you have like these edges that have weights. So the analogy here is that this is what these are, the convolution. So you'll be like learning, and of course, like initially you'll have some initialization here, but then you'll be learning it. But the thing when we did like something like this, transpose x plus b, this is what this convolution is actually doing. So this is analogous to that. When we did like these x, w transpose x plus b, and then got the output, this is what this convolution operation is doing. All right, let's see if there is anything else. People who are online, if you have questions, like feel free to type in the chat and I'll keep checking that as well. Let me see what this is before we move on. Yeah, so this talks about different types of convolution kernels. So you can like quickly go through this. Like, for example, it's a very nice one here that the kernel they're using is like by explicitly setting these values initially, it is able to capture the contrast. Like, and then if there is a high contrast between like different pixels, because if there's a high contrast, then like the pixels who are next to the middle one will have like extremely opposite values, right? So somehow we are able to capture that by using this kernel. So this is a nice article that actually talks about like what are different kernels that we can be, kernels or filters that we can use. But I just left it there because I wanted to talk more about the architecture of CNNs and eventually like how can we set the entire model up and how the learning process works. So moving on, the other thing that I wanted to talk about is the two more operations in that convolution portion that are known as padding and stride operations. And we saw this actually when we were looking at convolution. There are two downsides to this convolution operation. Let me show you what I'm talking about. Okay, so when we did this, okay, every time I forget. So when we were like, we had this like 6x6 image. Okay. And then I had this like 3x3 filter that I was placing on this, right? And so let's say this is the first time I placed my filter, right? And then the second time I placed it here, and then the third time I placed it here, and so on, right? And so by placing this, I'm extracting the information from these pixels. And if you think about this particular pixel here, this one, right? Or like this one, or this one, the corner ones. Now the interaction that these get with my kernel or my filter is the minimum as compared to a pixel here. Because this pixel will interact with my filter more than these corner ones. So this creates a scenario wherein like if there was some information that had to be captured on the corners, maybe it was captured, maybe it wasn't, as compared to like the pixels here, it like relatively speaking, it wasn't capturing as much as this one would have, because this filter, like imagine this passed here, and then like even when it went down, it passed here. So this particular pixel got a lot of I would say representation in my final convolution or my feature map as compared to these corner ones, right? So this issue actually is known as like the issue of corner pixels. And so we need to do something about it, right? And the other thing that comes up in these convolution operations is, of course, based on the choice of your kernel or based on the choice of your filter, sometimes you do lose some information because I'm like really downsizing my input. Of course, that's required because like we only started with that motivation that we need to do that. But sometimes with certain filters, it so happens that we just like tend to lose that information. And so what should we be doing in order to like deal with issues like these? So the first like solution to that is known as padding. And what we essentially do in padding is, let's say like my input was something. Again, this was 6x6. Okay. And I can like put another just like padded layer around this image. Let's say this was like size 1 on either side, and it has like no values, like it has zeros. I can put anything here. But the whole point of like having this padded layer around that image is that when I start putting my filter over these, right, because my filter is still going to be like a 3x3 kernel that's going to like overlap, right? But then my corner ones, like my corner pixels, will get more representation. So maybe in other words, you can think that like I have moved my filter a little outward, and then I'm like calculating the values, right? So effectively what I'm doing with padding is that I've created another layer, which actually did not exist in my input image, but I'm using that to compute my feature maps. Just because I want a more robust, I would say, representation of these corner pixels. So how does that impact your feature map calculation of their dimensions? Well, we have a formula for that. Now, because you've added this pad either side, right? And then I could have added 2 or 3, and then I should add 3 here as well, right? So this is how padding is done. Should be everything around the image, and then it has to be equal, right? So if we have done that, then the dimensions of your feature map are going to be this L, this was L by L, let's say, and then my filter was F by F, right? But then I've added these on either side, right? So how do I compute that? Well, you can do something like L plus 2P, where P is the size of the padding that you're using, minus F, and then the plus 1 stays. So this is how you can compute the size of the feature map. Now, the thing here to remember is that it's still the same formula, because earlier when I had P equals 0, then I just had L minus plus 1. So if we are using 6 by 6 input image, and my kernel or my filter is 3 by 3, and I'm using a padding of size 1, right? And if we compute the feature map, let's compute the feature map for this particular problem. So L is 6 plus 2 minus 3 plus 1. So that's 6, right? And so if you think about it, this is 6 by 6. My feature map is going to be 6 by 6 because I've added that padding. So that's kind of indicating something that I have retained. Somehow I've retained a lot of information from my original image. And in certain problems that helps, instead of thinking that we haven't cut down on our input size. In fact, in a lot of image recognition tasks, that is a helpful addition when we are doing padding. Okay, so that's a bad place to write, I just figured. So all I did here was minus 3 plus 1. All right, so that was about padding. It's more like the effect of not utilizing the edges has been somehow diminished or reduced, or we are taking care of the edges, right? Okay. So then there are different types of paddings. As I said, you can have different values for P, and there are certain standard known paddings that you should be using for certain types of problems. So all of that information is there in one of the papers that I have put in the, I think in the notes at the bottom. All right, I need to add a few slides and then we can. Okay, the other thing that I wanted to talk about was striding. And I mentioned striding earlier when we were talking about the convolution operation itself, right? So I said we are striding by 1. Now, sometimes what happens is that we will eventually this model will be learned by my backpropagation and my gradient descent. And so the number of parameters that I have in the model is huge. And so basically with striding sometimes I can make it. Yeah, so here. So I can change that striding effect. If I see, let's say there is an image that's not capturing much when I'm moving by 1. Maybe the features are spread out. Let's say there is a picture of a desert or something that doesn't really change as much with every pixel. If you understand what I'm saying, let's say an open field that has green grass and not much is changing. So there is no need for me to keep striding for every pixel. Rather than based on my input, I can adjust my stride. So here is an example of how the striding works. Here the stride is size 1, right? So let's say I want to create a stride of size 2. How will that work? Let's see. Okay, so here I'm moving this by 1. And instead of moving it by 1, the next time I place my filter would be somewhere here and then somewhere here, right? And then the next time I move my filter, I'll start from here as I move downward and then skip 2 and then move downward and so on, right? So how does that help me? Well, that helps me because I'm not like, I'm of course able to capture the spatial structure of different pixels, but then I don't want like the same pixel to be represented so many times and be like interacting with the filter so many times because of a lot of reasons. I don't know. Maybe that's how my problem is set up. And so I can decide that stride size. And the size of that stride also impacts the output size of my feature map. Okay, so here is the final formula that you should be using for your like output. And so my output will be something like this. The dimensions of my feature map are going to be, so that stays L plus 2P minus F, all of that stays. But what you have is that divided by the stride. And it's going to be the same for the second dimension as well. Usually they are squared, so. And yeah, so like the only issue that might come up with this is that sometimes it's not like completely divisible, and so we cannot have dimensions that have decimal. So usually the convention is to take the floor of this, and so this is going to be my out. Okay, does that make sense? So this is going to be the mean by output I mean like the dimensions of my feature map. And this entire, like whatever we are doing, convolution, striding, padding, we are doing that to extract relevant features so that we can use them to train my network, right? So everybody's on the same page as far as like this idea goes. All right, so now we know like a very simple idea of like reading a grayscale image, performing the convolution operation, maybe even doing padding, striding, depending on the problem, and then like using that further, right? So now I'll add to this like the RGB image thing, and then talk a little bit more about this thing, what's happening here. So there are a couple of things that have changed here in this picture, if you think about it. This is like known as convolution over volume. So first, let me not go into like so much of complication. First, let me show you a basic idea of what I'm. Oops, that's not what I want. I just wanted to make it bigger. Okay. So now let's assume that I have an RGB image. Now we've been talking about the grayscale one until now. And so whenever you think about an RGB image, think of these like different stacks or a cube that exists, right? So the cube is here. And then the important thing here is that the filter that you're going to use should also have like the same depth, right? So this thing sometimes is known as the depth or channel. So the number of channels should be the same for my image and my kernel, both. Okay. So here maybe I'll take like a 3x3 filter again. And the convention is usually like take an odd filter, right? So 3x3x3, because this depth should be the same for like this and this. So that's that. Now remember we were placing this filter on top of this, right? So instead of placing the filter on top of the image, I'm like placing a cube here, if you know what I mean, right? I'm placing a cube because this is also a cube and the depth is the same, so I can do that, right? And so when I'm doing that, right, I'm placing a cube. Do you think this output, this feature map will have some kind of a depth as well or channels at all, or no? Or if yes, then what is going to be the dimensions? Just imagine that I've placed a cube and then I'm moving that cube here. And let's say the stride is 1. So I'm just like moving them 1 towards the right, and then I start moving them towards the bottom. And so I've placed a cube. And the way we are doing the convolution operation is that, remember, we are taking the dot product, but then I'm taking the dot product of the entire, like all the 3 and adding them to get just one value. So if I'm doing that, right, I'm getting just one value. I don't think I'll have a depth here, right? Just try to visualize. This is an important aspect of convolution. Just try to imagine this. Of course, I've placed a cube here, and maybe I'm not like doing justice to this drawing, but because the depth, this one and this one, they have the same depth. So when I place the cube, it's actually capturing all the 3 stacks in like one operation. The only difference is that I'm going to multiply each of those values with the corresponding columns here. Right? So think about like this one will have like some certain set of columns that will be multiplied by the top R, right? And then this one will be multiplied with the G, and this one will be multiplied with the B. So I can still like add them up or sum them up and get like a single value. Right? So I don't think this one will have a depth here yet. Okay, so we said that these filters or these kernels are somehow capturing some particular aspect of my image, like maybe brightness, maybe contrast, maybe vertical edges, maybe horizontal edges. And so like if you think about one picture, let's say like somebody's picture, like somebody's photograph, right? It has more than those like attributes. It does like, if I'm doing like facial recognition, I'm not done by just like extracting like vertical features or horizontal features. There is more to that. Agreed? Right? So what we need to do is like, of course, I understand that I'm extracting all the features using this convolution and everything. But now if I'm using this like RGB image again, and I have like a filter that captures vertical edges, maybe I also need a filter that captures horizontal edges. And maybe I also need a filter that captures maybe contrast all at once, because I don't want to miss that information out, right? My image could be more complex than just like vertical lines or horizontal edges, right? So the way we deal with that is exactly like this, that you can have like a filter 1, you can have a filter 2, you can have a filter 3, and so on, depending on the task. And now, just now we talked about the feature map. Now, as I'm moving, like let's say filter 1 over this image, right? I'm getting like some feature map here, and I'll have like one value assigned to each of like 4x4, whatever I'm using, right? And then I'll have another feature map that comes out of like the interaction of filter 2 with this image. And so I'll have another feature map, right? Because that is going to be like, the first one is extracting vertical lines. The second one is extracting horizontal lines. The third one is extracting contrast, right? And so I'll have all these features here, depending on the number of filters I have. And then eventually what we do is that because we have like all these features, we stack these together to have a final feature map that will be used further in my network. So if I've used 3 filters, right, I'll have like three of these. And so the dimension of this would be, as I said earlier, like L plus 2P minus filter plus 1 for S, right? That is going to be one thing. And then like the second one is going to be the same. So, and the third thing is going to be the number of filters. The number of filters that you used is going to be the dimension of like my feature map finally. I'm using 3 of them, so I'm going to stack these 3 of them. Now I'm going to show you a much like cleaner picture of this, because I know I made like some really messy, it doesn't let me. How do you, yeah. Yeah, so here it is. This is what we were talking about. Okay, so here is my 6x6x3 image, this one here. And then I applied 3 different filters. And for each of the 3 filters, I got one output. That is my feature map, right? But then I don't want to lose any of this information. So I'm going to stack these feature maps one over the other. And so this is obviously going to be L plus 2P minus F over S plus 1. And again, this 4 also came out of that. But this 3 came out of the number of filters that I used. Because if I was using like 5 filters here, then I would have like a stack of 5 and so on. Right? So this is something that's important to remember, that the third dimension of this feature map depends on the number of filters, directly depends on that. All right. So is this like clear to everyone? Should we move further, or do you want me to explain it again? Is this like, are you okay with this part? Okay. And probably the implementation part is going to be the easier part, because as I said, there are like these known networks that exist and you just have to pick them up and use them. But I think it's important to understand what's going under the hood, because I think like when we are solving a problem, it helps, right? What's going inside. All right, so moving on. Okay, I wouldn't jump into pooling yet because I wanted to talk a little bit about 2 or 3 things more. So let me quickly go there. Okay, so why is this a neural network, and what are some of the analogies that we can draw from the feed-forward networks? Because this is important in order to understand how backpropagation works in CNNs, right? So let's try to understand that. And so what usually happens in any CNN is something like this, that you have an input image. Let's say I have like something like this. Let's stick to our 6x6 thing. And then I have like some filter here. That is like filter 1, let's say filter 2. And let's say we perform the convolution operation. Usually when we have like this output here, we pass it through non-linearity. Again, for a lot of reasons, for getting a better idea of the features, for make them more usable for like my feed forward and my back propagation. The convention is that we pass it through a ReLU. So basically, most of the time we use a ReLU. We can use some other nonlinear function as well. So here I'm going to do something like this. So remember my feature map that was like 4x4, and I usually like you can just sum up a bias if required. Sometimes it's required, sometimes it's not. But I'm just like writing a more generic kind of and 4x4 plus B2. So I pass it through a ReLU. Usually a nonlinear function could be sigmoid, could be something else. Usually it's like a ReLU. So whenever we do a convolution operation, the thing that you should remember is we don't have like just the dot products, but we also pass it through a nonlinearity function, usually a ReLU. And then we get that 4x4 final feature map. Okay. So this entire thing, this input and then this convolution and then passing it through this is considered to be a single layer of my CNN. This is one layer of my CNN. And let's try to draw an analogy between this and the feed-forward networks that we've seen before, right? So in the feed-forward networks, if you remember from our notation, in every layer, I was doing 2 operations. The first one was sum the inputs, right? W transpose X plus B, and then pass it through a sigmoid, right? So pass it through a sigma. So those are the 2 things that we are doing. If you think about that, like high level here, that's exactly what we're doing here as well, with like certain modifications, of course. So let me write that down and see what's going on. So in any layer L, or let's say in layer number 1, this is what we were doing. And A0, I'm writing A0 for X. So input X, either you can like denote it by A0 or X, that's fine. I'm writing it with A0 because remember, every time we were moving forward, we were denoting it by an A instead of X, the output of the previous layer. So that's why I'm writing it as A0, and this is B1. Right, so this was the first operation that we performed. And then the second one that we did was compute A1, which was usually the sigmoid, and pass it through Z1. That's what we did like in every layer, right? So now if you look at the CNN, this here is my A0 or X. My input is my A0, right? Now looking at the convolution operation here, this one here, this exact thing, like this filter thing is exactly doing something like this. Let me write it. X0 or A0, let me write it down. So this is doing this part here, right? That's exactly what we're doing. And then this thing here, this part here, is actually this Z1. So this entire thing is Z1. And then if I pass it through a ReLU, then I get an A1. Because A1 is also passing it through, like maybe we had a sigmoid earlier, right? Instead of a ReLU. But that's exactly what we were doing. Passing this Z1 through this, like some non-linearity. So that's what this part is doing here. And that's how we get this outcome for the next layer. Right, so there is a huge like analogy or huge like relationship or similarity between both the CNNs and the feed-forward neural networks, right? And this is why is this important? This is important because like going forward, we will try to see how backpropagation works with these as well. All right, let me see if I missed anything before we actually jump to. Okay, I think I've talked about the dimensions. Let's see. Okay. Before I jump to the pooling part, there is a very nice article. Yeah, I would highly recommend everybody reading this paper that I have provided a link in the lecture notes. And this actually introduces convolution neural networks and like the motivation behind them, the structure of the CNNs. And more importantly, this one here is, okay, this is fine. Yeah, and this also talks about like, it points out to a very nice thing why we need, like, we cannot use artificial neural networks and why we are using convolution neural networks, because you have such like humongous amount of data with every image that it might at times lead to overfitting. And so we are also dealing with that when we are like doing these convolutions. So that's that. And yeah, this is the thing that I wanted to show you, and I'll go through that. But this is high level what a very simple convolution neural network looks like. So, and this is like using the MNIST. So that's if you can see the input. Let me make it bigger. This input is like a zero, handwritten zero image, right? And then you have like convolution with ReLU. So everything that step that we talked about, ReLU, and then the filters plus that bias, right? Whatever we got out of the convolution operation, that is done here. And then there is this extra thing that's done, that's pooling. I'm going to talk about that. And then finally, we have the fully connected layers. So how does that all work out? Let me show you what like how we set up these different layers and how do we get the output? Because think about like what all classification, like what all tasks are we doing when we are doing image recognition? Like it could be classification, it could be regression. And so how to get that? Because now we understand that this is like one layer, but how does that like convolution and moving from one layer to another helps us? So let's draw a picture here. And that's like motivated by this picture. That's why I wanted to show you that. Let's draw this. Okay. So, okay, let's assume we have like some input, 3-dimension or RGB, right? And let's say this is like some dimensions, 39, 39, 3. This is my X, right? I'll apply some filter, some striding, and this is like layer 1, so filter 1. It could be like, or depends like how many filters we are using and the dimensions of the filters. So let's say I'm using like 3 filters, right? And I'm using some stride. Stride is 1. So this is like the usual one. And there is no padding. So we have to specify all these parameters. I'm like showing you what is like the feed forward step in a CNN, right? So this is the first step. Then we extracted some feature map, right? And we're going to have the dimensions of that. Now notice what's happening in every subsequent step. The length and the width begin to go down usually, and then the depth starts to increase because usually like let's say filter is size 3 by 3, and let's say I'm using 10 filters. If I'm using 10 filters, then this depth is going to be like 10 because I'm capturing 10 different aspects from that image. So that's the like high level idea of what's going on. Of course, I'm shrinking this and this. It won't be 39 by 39 because I have that formula L minus F plus 1, right? So of course, this is going to come down to maybe 37 or something, but this is how this works. And next, what we have is like maybe a pooling layer, which I'm going to talk about just now. But from the information that we have right now, we can have many such layers. So I can have like another set of filters, let's say F2, and let's say like I'm using 5 filters now, and then some other padding, some other striding, and then I get like something like this, and so on, right? So this is how this works. So you can have like multiple layers. Eventually, like after 2 or 3 layers, what you're going to do is you will have some kind of like this kind of a structure, which you can just like flatten out and like just like create a vector, a single dimension with all the pixels such that they have captured all the relevant information. And then once you have that, you can apply like a softmax or like a sigmoid or like any function that you need in order to like, let's say, predict something or maybe classify something or maybe it's a regression problem. So compute that. So this is like high level how this goes from the input image to the final classification thing. Now we've missed a couple of things here. That's like there is a pooling layer that's also added. We haven't talked about that. So I wanted to first cover like high level how the flow happens and how we make the predictions. So if that like high level flow is clear, then we can move on to adding more aspects here, here. Like we can make it more complex because we want to capture like other aspects of image processing. Okay. All right. So that's that. Okay. So as we go ahead, you must already be thinking that like in all these layers, and every time I'm creating a feature map, look at the number of parameters that are being generated because eventually I'll be using those parameters in my backpropagation and everything. Plus, like even a lot of hyperparameters. Because I just said, like maybe I'm using 10 filters, right? I said maybe I'm using 5 filters here. But like I don't have a good answer to how many filters I should be using at every step, right? And then maybe I'm using padding or maybe I'm not using padding, right? Or maybe I'm using a stride of 2. So all of those are hyperparameters. And these are like a very big issue when we are dealing with CNNs. And there is like a systematic way of dealing with that. And that's what I'll be discussing in the next lecture. But like keep in mind that these hyperparameters have like this huge effect on your output, on the quality of your output. And so there are systematic ways of dealing with this, right? But remember that this is like exceptional in the sense that we have to tune a lot of things. And in addition to that, and let's think about like the gradient descent. Let's say I'm using this, I'm training this using some variant of my gradient descent. So the gradient descent itself comes with like so many hyperparameters. So it just like keeps adding. And so there's a systematic way of dealing with it. All right. Now, until now, whatever we have discussed in a CNN is that each of these has like these convolution layers. Every layer in my network was a convolution layer, right? But there are 2 other types of layers in a CNN. So like the first one is the convolution layer that we just saw. The second one is the pooling layer. And the third one is the fully connected layer. So there are these 3 different types of layers. And so what exactly are these pooling layer and fully connected layers? And your CNN is not complete without these. And first of all, why do we need pooling at all? Let's go back to the lecture slide, lecture notes and see why we need them. Okay, this takes forever to come back. All right, and let's do that. Let's take a 5 minutes break before we begin with, because I think this is going to take a little bit more time, understanding pooling and then the overall architecture. So let's take a 5 minutes break and then we can get started. Okay, let's get started again. Late, the question that you asked is what happens if the position of the features are rotated or flipped, and or can pooling help with that? So pooling is more to reduce the dimensions of the maps that we have created and make it more robust. And if you're trying to deal with like rotated or flipped images, I think the convolution filter itself can help with that in most of the situations. But let's talk a little bit more about like how pooling works, and then maybe your question can be answered better. So what exactly is pooling? As I said, that we have applied, like, so we have filters, right? And we have applied them to images and extracted some important features from them, right? And sometimes what can happen is that we are, again, like one limitation is that we are trying to capture every precise position of like every pixel out there in my image. And sometimes like that might not be like useful in terms of like the computational power that you need to train your network and to run your model and other things. And so there is an extra layer of pooling that's applied to that feature map. And there are different techniques of like doing this pooling thing. And let me show you how we do that. Let's say I have more slides. Okay, so one very common way. So one like very common pooling method is known as like max pooling. And I think you'll find that when you're implementing it in TensorFlow or Python, you'll see that there is this option of like what pooling you want to use. And usually people use max pooling. And how it works is that let's say I have like this feature map, some, I don't know, 4x4 or 6x6, like whatever it is, depends on like which one we are using. And what we try to do is we try to extract like the information from like, let's say we are interested in this part, right? And then we have some pixels here, some pixel values here, 1, 2, 9. And what max pooling does is that it's going to get some reduced dimension of this based off of like, what is the max in this particular square, or maybe like I'm taking this part. Like again, those are all hyperparameters. And let's say we decided that this is going to be like a 3x3 matrix. And I have, like, I don't know, 3 again. So what is the max in this one? The max in this one is 9. And so that's what I'm going to take, right? Or maybe I should have taken a 2x2 because then that evenly divides this 4x4, right? And so I'm going to take like the max of the topmost corner, which is 3. And then maybe that there is something here, 1, 2, 5, 4, 8, right? And so here the max is 9. So 3, 9. The max in this bottom one is 8, and the max in this is 5. Idea being that I'm just like trying to capture the most dominating feature from those, and then reduce the dimensions of the feature map so that my training and my complexity is reduced, right? And definitely depends on the task at hand. Like sometimes it works really well, sometimes it makes you lose features. Of course, like this is a hyperparameter. It's a very important hyperparameter. And the other thing that I wanted to like point out here is that these are the values that I get from my features, and these are not learned in my learning algorithm. These are not learned, right? So like setting up the size of this and the number of like the pixels that you're picking up, it totally depends on like how you want to set up your pooling layer, right? So in other words, it's just like shrinking the size of your features. That's all we're doing here. And another thing is that there is another thing that's known as average pooling. In some of the networks that we'll talk about on Friday, we'll see that average pooling is also used. And what average pooling does is that I'm going to take like all these values, sum them up, compute the average, and that is going to be this value. Right? And similarly, I can compute the average for the rest of them. Okay, so now having talked about convolutions, having talked about pooling, how do we set up my overall network? And then how do I make it, like how do I train it? And in order to understand that, let's look at this example. And I want to, so this is taken from MNIST, and this is a known network. I have like a picture of that in the lecture notes as well. So So this is LeanNet 5. I'm sure you must have seen this somewhere. If not, like once you start working with CNNs, you'll come across that. So this is one of the known CNNs. This is like one of the older ones. And the basic structure of this is something like this. So let's say I'm trying to figure out from my MNIST data set. I have like MNIST, and my input image is 9, right? And I'm trying to figure out like what digit this is. Right? And the way this is set up, this LeanNet, is that you have filters, and there are 6 filters in the first layer. And the size of the filter is 5. So 5 by 5, 6 filters. And the stride is 1, no padding. And you get like the first feature map, right? And this, like usually in convolution neural network literature, is denoted by conv. So this is like the first convolution layer. And because this is the first one, so we usually denote it by like saying conv1, right? And then you apply pooling. So right after convolution, by this I mean the convolution computation plus the nonlinearity. So the ReLU is also added. And then the output that you get is going to give you like something. And so you want to like further reduce it. And so you'll apply, let's say, pooling. And let's assume I'm applying max pooling, right? So everywhere I'm applying max pooling. And here I'm going to get like something else which has like reduced dimensions, but definitely more here or the same, depends on like what we are using. Usually reduced dimensions, because that's the whole point of using max pooling or average pooling. And so once you're done with that, so this is also known as like pool 1, right? And then you'll have like another convolution layer with some filters, and here there are 10 filters that are applied. Now you must be like thinking how do they come up with that? And that's the whole point of like knowing the known networks, because like you can go on forever like changing the configuration of this, right? And so F is 5, S1, you get another conv2. So this is known as conv2. And then another like pooling layer, max pooling. And then you get like another pool 2. And once we are done with like these 2 layers, usually these 2 layers having like conv1, pool 1 as one layer, conv2, pool 2 as the second layer. Once we are done with that, we have like a pretty like flat structure here, and usually we flatten that out. If it's not flat enough, we flatten it out and we convert it to a vector, right? And so the thing is that you'll have like these values that your network has generated in a single dimensional vector, right? Now I can use these features or these values as input to my feed forward network. And so that's what happens next, believe it or not. So you have something that's known as a fully connected network. So these are fully connected layers, and you usually use them as, so this is like FC1, fully connected 1. Maybe you can have another layer which is fully connected 2. And you specify the number of neurons, which is another hyperparameter. So you specify, let's say you're using 84 neurons. And then similar to like a feed forward network, you'll have these as inputs to those neurons, right? And so imagine like similar to like a feed forward network, you'll have like 1 or 2 layers of this fully connected layer. So you do have a fully connected network towards the end, after the convolution, the pooling, the extraction of features is done, right? So maybe you can have like 2 fully connected layers, and then finally the output layer, which in this case, because this is like digit recognition, digits are from like 0 to 9. So maybe a softmax, right? Because softmax allows us to classify more than 2, and then the output. Okay, that's already so tiring, right? So this is like a typical example of a CNN. And this is like one of the earlier ones, the ones that we're going to like look at on Friday have like more complex structure to that. But I'd still say high level, the idea stays the same. The first thing, I have images. Let me extract information. Let me not lose the spatial structure of the pixels and their relationship with one another. And let me use it in a network such that I can extract most of the information and do proper classification or regression, right? That's the fundamental idea. Again, like this issue of like hyperparameters is quite important, and we will definitely address that. But I would quickly go over like how do we train a CNN, right? So we have looked at all of this, but how do we train it? And so let's quickly write this. So let's say I have an image and okay, and then we go con1, let's say pool one. Sometimes like this you will see in literature, you'll have something like this, like CRP telling like this is the network. So basically C is the convolution, R is the ReLU, and P is the pooling. And so if like you have something like CRP, this is telling you this is the structure of your neural network, right? So this is like telling you this is convolution, ReLU, convolution, ReLU, and then pooling. So, and then like the fully connected, how many fully connected you have. So similar to that, I have, let's say, this, and then conf2, and then pool2, FC1, and FC2, and then finally I have the sigmoid, or maybe the softmax, and then I get this y hat, right? So after all of that, right, I have the y hat, and I need to learn all these weights and all these parameters that I have. The rest of the stuff stays the same, except that how am I going to learn through this like convolution operation? And one thing that I like to point is that it's just like one more derivative that's added. That's it. Otherwise, the rest of the back propagation works exactly the way we saw that in the feed forward network. Except that like in every like convolution layer, you'll have an extra derivative because you'll be deriving it like, so basically you have like a filter times the image. And so you'll have to propagate through that filter and then the image, if you understand what I'm saying. So there's a nice article that has a pictorial representation of that. We're going to look at it. But here, let me just write this down. So the cost L is going to be 1 by M, the number of pixels, and Y hat, YI, and sum all of these up. And so again, we use gradient descent. And you can use any variant of gradient descent to train this network and back propagation. And by the way, back propagation is very similar to what we know. So there isn't a lot of change in back propagation because we have this analogy that we drew between like a fully like this complete CNN and like the existing feed forward networks. So as long as you can draw that analogy between the derivatives dz and dA, remember, that's exactly the same thing that's happening. In addition to that, you'll have like a DC, that's like you will be computing like a derivative through the convolution. And the only thing that's changed here is that you have like many filters. And so you'll have to propagate through all those filters. And so the number of parameters is huge, of course, right? So let's go over that article. But before that, a few things about convolution and why we have used convolution. The first thing, let me write it down actually. Okay, so one of the first thing is parameter sharing. So why do we need convolutions and why are we using convolutions? So let me just write why convolutions. So the first thing is because they allow parameter sharing. Well, what does that mean? Okay, so the same filter will be passed through the entire image, right? So the same filter can be used and reused to detect the same features in your image. So here we are using some kind of parameter sharing in the sense that you don't need like for every different part of the image, you're not using something else, right? So that's one thing. And of course, like as we talked about, the motivation behind using convolutions is that like the number of parameters to be estimated goes really down, right? So the number of parameters to be estimated goes down, right? And the third thing is now each layer has small, so as we are moving through these convolutions, each layer has like the smaller number of parameters that need to be like learned, right? Because that's what we're doing in every convolution layer. With every filter, you're reducing the dimensions of like your output in some ways, right? So those are some of the important reasons of why like we are using convolutions. Going back to the training part, show you. Okay, why does this takes? Okay, so here is, I think we already talked about that. Here is the LeNet 5 that I was talking about. And so this is like one of the earliest CNNs. And this is the structure of like this. This is a detailed representation that this was an image and then the convolution, then the next feature map. So three, I think that there are pooling and then more. So C is essentially the convolutions that are happening. And then you have like three fully connected layers actually. Right. So if you think about it, like let's actually think about like different architectures in CNN. Just like changing that configuration a little bit can give you so much different results. Because like what's happening with every subsequent convolution, I can just like keep on adding those convolution layers. But then I'm also adding to my computational cost. I'm also adding to my time. So basically there's a trade-off between like how complex I can build my model and like how long does it like take to train and like what are the system limitations when I'm running my algorithm and so on. So that's why hyperparameter tuning is an important aspect of CNNs. Okay, so going back to backpropagation, this article actually talks about like really well. And I would say like the rest of the stuff stays the same. I would ask you to focus on, okay, this is something that we already know. Not this. So what happens in the convolution layer? And this actually shows us what happens in the convolution layer. Because you'll have two things to think about. Okay, so this is just showing up that this is the input and this is the filter, right? And so we know how the convolution happens. And so the output was, or the feature map was computed using this input times filter. And so when we will be computing the derivative, we have to take care of this, right? And so there was a nice, yeah, this is how the derivatives are passed through the convolution layer. So now think about this circle, this convolution thing as that box that we talked about when we said convolution with the nonlinearity applied to it, right? So there are two things. This like we are computing the loss with respect to the O or the output of the convolution. And so when we are like going backwards, I am going through the filter as well as like to every image. So I'm propagating through both of them. So again, like chain rule applies, you're computing everything that we've computed before, except that like the local gradients for like a given convolution layer is computed based on like the input X and based off of the input filter. So the derivatives are like computed, the local gradients will have like um, the derivative of this output with respect to X and the derivative of the output with respect to F. Because using chain rule, I can then compute the derivative of the loss with respect to X and the derivative of the loss with respect to the filter. Because also think that that filter was in some ways an input to my convolution layer. So there, like this backpropagation will go both ways. But then this is nothing new again. Because if you think about like the feed forward networks, I was passing through all those weight edges. I was back propagating through all those edges. So if you think about it, this is nothing new that's happening here, right? Those filters are my weights, except that those filters have some elements in them. Just like try to visualize. So nothing has actually changed, right? So again, back propagation is still the same, very much the same. So this article really like gives you the details of like how back propagation works. Again, we have looked at this before with feed forward networks. It's the exact same thing, to be honest. Like if you have time, just like quickly go over this. And one paper that I wanted to bring up again. Now this one actually talks about like how gradient descent works with convolution neural networks and like some of the variations of gradient descent with CNNs. But the fundamental idea still stays the same. You can apply Adams algorithm, or you can apply RMS prop, or you can apply other like known gradient descent variants to the back propagation or to like the learning process in a CNN as well. So this one is, I think, first talking about learning from data. Yeah, so let me see if they have. Yeah, sometimes you see this like term written as like subsampling along with convolutions. And striding is sometimes known as subsampling or downsampling. So if you get like confused with that term, it's mostly like referring to uh, bringing down, like, right? So why am I doing striding? Like if I want to move forward, I want to cut down on some of the features that I'm like just repeating. So that downsizing, that subsampling, sometimes in the in a CNN, if you see that, that's usually because like we have added like some kind of striding in addition to like my pooling and my convolution. So that's that. And else. Okay, so there is nothing additional to what we already discussed. But yeah, this is another like good paper to at least go over and see like how to train a convolution neural network. So this is important, and this is paper number 2, by the way. In paper number 1, I just wanted to give you an idea of like how rich feature detection or edge detection is done with different types of kernels. So if you're interested, you can go over this, but my recommendation, like my high recommendation, is do go over like paper 2. That's an important addition to like whatever we discussed today. So yeah, that's all that I have for today. In the next lecture, I'm going to talk about hyperparameter tuning in CNNs. And also we'll discuss some important known CNN architectures that you can utilize as they are. And like, depending on the problem that you're trying to solve, you can utilize those and then go from there. Okay. So that's it from my end. If you have questions, please ask. Otherwise, yeah, that's it. Thank you so much.